Hello, everyone, and thank you for attending today's webinar, Demystifying AI for Petroleum Engineers. Today's event is made possible by the technical partnership between the Society of Petroleum Engineers Digital Energy Technical Section and NVIDIA, which has led to nearly 1,000 registrations on LinkedIn. Before we begin, we wanted to familiarize you with the On24 platform. At the bottom of your screen are multiple application widgets. All the widgets are resizable and movable, and you can expand your slide area or maximize it to full screen. If you have any questions during the webcast, you can submit them through the Q&A widget. Our Q&A moderators are standing by to answer your questions, and we'll try to answer all of them by the end of the event. In the resource list, you will find helpful materials that you can bookmark and download. We encourage you to explore these to learn more. In the Help widget at the bottom of your screen, you can find additional answers to common technical issues. Finally, an on-demand version of the webcast will be available approximately 1 hour after the webcast and can be accessed using the same audience link that was sent to you earlier. Let's begin today's webcast.
Hi everyone, and welcome to Demystifying Deep Learning for Petroleum Engineering. My name is Peter Dykes. I'm a solutions architect here at NVIDIA working on simulation and applying deep learning solutions. If you have any questions today during the presentation, just feel free to put them into the chat and hopefully we'll be able to answer them as quickly as possible. At the end of this, hopefully you'll have a better understanding of the basics of deep learning, the types of problems that we can solve with deep learning, and where it could be applied to petroleum engineering in the future and where it's being currently applied to petroleum engineering. Before we get started, I just wanted to quickly go over the agenda for today. To start, we'll just go over a high overview of deep learning and machine learning, and then wanted to quickly go into why it is seemingly all of a sudden that we're seeing this massive explosion in the use of deep learning and why some problems require the complexity of deep learning. Then later we'll dive a little bit deeper into the different types of problems that deep learning can solve and the different techniques that you can use with deep learning, and then where it can be applied specifically in the petroleum space. And then briefly at the end, I'll touch on some ways to get started and different resources to learn more about deep learning and kind of get your feet wet. AI and deep learning have been making huge leaps and bounds in recent years. As an approach to artificial intelligence, deep learning is showing itself to be stunningly effective across a whole range of domains by transforming the way computers achieve these perceptual tasks, such as computer vision or pattern detection, speech recognition, all the way to behavior prediction, across a whole range of different tasks. And deep learning is beginning to affect a whole range of these industries and is working behind the scenes in many places that you might not even realize. So for example, within robotics and autonomous vehicles, deep learning perception systems are being able to train to perceive the world around it in order to make these intelligent decisions. A more concrete example would be a car, for instance, must be able to recognize traffic lights or lane lines around it in a bunch of different conditions in order to drive correctly and safely. And this is often done nowadays by training these deep learning computer vision systems to recognize these different objects around it. And then we can go to healthcare, where deep learning is being used in many different areas, from genomics to drug discovery. Everywhere internet services are utilizing deep learning behind the scenes, so for NLP tasks such as speech recognition or translation with these large-scale language models that are coming out. Large-scale recommendation systems are being trained on people's past behavior to try and figure out what's the best recommendation to serve up to the user. So this could be anything from the next video option on a video streaming service or a product recommendation. So you can see deep learning systems are being broadly adopted across many different areas. Before we dive too much into the content, I just wanted to quickly touch on the role that NVIDIA plays in deep learning and where we come into the picture. So in the beginning, NVIDIA specialized in GPUs on the graphics sides for gaming, design, and rendering, and we're still heavily invested in this area, and it's the bread and butter of NVIDIA. But it became apparent that the parallelization properties of these graphics cards that were used classically for rendering lent themselves really well for high performance computing problems and AI problems, which eventually led NVIDIA to begin working in these types of areas. As we'll see, that being able to scale up these deep learning algorithms with massive parallelization is one of the core ideas for why it has all of a sudden had this explosion in success and began to innovate at such a fast pace in these recent years. Begin, I think it's good to start at a high level of what we mean when we're talking about deep learning and where it fits into the picture with these other terms you might hear, such as machine learning and artificial intelligence. So on the screen, we have a Venn diagram that gives a good snapshot of the intersection of these three different areas. It's not perfect. It's missing some of the nuance between the different areas, and a lot of it's just semantics, but for our purposes, it's a good, useful, high-level simplification. So to start out at this high level, AI can be seen as a science of trying to mimic human abilities in order to solve certain problems. So AI uses data and technology to solve these tasks that classically required human experts and ability. Now, if we go down a level, machine learning can be seen as a subset of AI. This is where we teach a machine to learn from data rather than by explicitly programming it to do a specific task. So this might be in the past where we used expert systems to solve the problem, where we had humans generating rigid handwritten rules. Now, an ML model looks for patterns in the data and tries to draw out conclusions or answers kind of like you or I would. They're trained by being provided examples in the form of data, and then using a combination of statistical methods and advanced algorithms, they learn what to do from these examples. And then as these models are exposed to more data over time, they continue to evolve and hopefully improve. And you can see here statistics at the heart of machine learning. Now that we've defined machine learning, we can go down a level where deep learning can be seen as a subset of machine learning. And this is where we use artificial neural networks to learn from large, vast amounts of data. So deep learning really shines in areas like computer vision or speech or natural language processing. And deep learning is also very good at extracting these insights or patterns when they're given large and vast amounts of data to learn from. So when a data science goes to tackle a problem, they might typically experiment with a bunch of these different techniques to find the one that best solves the problem at hand. And we'll see a little later on, we'll go into these different techniques and algorithms that a data scientist might experiment with day-to-day work. Before we go any further, I just wanted to clarify a few things. As we've seen, machine learning and artificial intelligence aren't the same thing. ML is a technique that is used within AI. It might seem also that ML is just statistics that's just been rebranded, but ML uses statistical techniques, but it's also a larger set of powerful algorithms that might use some statistical techniques. Another common myth is that ML and machine learning is just trying to replace all humans at their job. This is not the case. More often than not, machine learning is not just trying to replace a human task, but is more often being used alongside human workers kind of to solve the problems more efficiently. Now that we've gone into it at a high level, what we're going to be talking about and what deep learning versus machine learning versus AI is, we're going to go into what are some of the classic data science techniques and how those differ from machine learning. This is just a basic Venn diagram that tries to broadly summarize data science and some of the subdomains of data science. It doesn't completely cover all the areas, but does a pretty good job covering most of the big areas. So within the broad data science field, predictive modeling, which is what we're going to go into a little bit more, is the process of trying to use past data to predict future outcomes. And there's a number of different techniques that you can bring to try and solve these types of problems. And we're going to highlight a couple key techniques here that are statistical, machine learning, and graph. So this is just to set the stage of what some of the classical data science techniques might be. So we're just going to start from the classical data science techniques with statistical techniques. This is one that's probably familiar to a lot of you. So in statistics, it's trying to collect and analyze raw data to understand the relationships within that data. So statisticians have been using different techniques to understand data for a very long time now. Long before artificial intelligence or machine learning were being used. Here we have linear regression and logistic regression, which are examples of statistical techniques that are commonly used even today to build predictive models. They're computationally easy to train, they're interpretable by humans, and this makes them very attractive in a lot of different industries, such as healthcare, where, for example, a doctor might need to understand why an algorithm is predicting or recommending a certain outcome. Another more classic data science form is graph analytics, and this is where we might represent our data as a graph, where we have nodes with certain properties, edges between these nodes, and then there's weights on the edges. An example of some graph data might be a city where nodes are addresses, and then we have edges that represent the roads connecting them, and the weights on these edges are the distances. The internet can also be seen as a graph, and graph analytics have applications in many different areas such as physics, biology, or marketing. And now even graphs are being merged in with deep learning with the emergence of graph neural network techniques. So now that we've set the stage kind of with what are some of the more classic data science techniques, just giving a couple examples there with statistics and some graph analytics, we're going to dive more into what we're talking about today, which is machine learning. So this is a great quote that kind of distills what the essence of machine learning is and when we use it and why we need it. So the quote is, "A pattern exists. We cannot pin it down mathematically, but we have data on it." And this is a type of problem that arises a lot in many different industries, and this is where machine learning tends to excel. Now we're going to dive a little bit deeper into the components of a machine learning model and what is required to create a good ML system. So the key feature of machine learning, of course, being that we learn from data without being explicitly programmed to do so. So the figure on the left, taken from Gartner, this is an example of how data from a variety of potentially different sources might be fed into a machine learning system. This is a very broad view, and it's not exactly going to apply to every industry or the petroleum industry. But the general idea that you're supposed to get from it is that to build a successful ML model, you need data and you need lots of it. Along with these large data sets, you need data processing tools. You, of course, need the powerful deep learning algorithms. And then another key component is that it needs to scale with the amount of data, so you need the compute that goes along with it, with these large algorithms and large data sets. And you also need the human element of it, which is the data scientist, which brings the expertise in order to build these machine learning systems. So here we're beginning to break down machine learning a little bit more, and we'll go a little further into these three different types I'm about to mention. But at a high level, there's three different kinds of machine learning. You have supervised, where you have your data and it comes along with a label that you're trying to predict. And this has use cases in demand forecasting or recommender systems. The next type of machine learning is unsupervised, and this is where you have your data and it doesn't necessarily have a label. And you might have use cases in customer segmentation or fraud detection. And then there's a third set being a more advanced, which is reinforcement learning, where you're trying to make these sequential decisions by taking actions, and you might only get a feedback of having a reward. And this has use cases in robotics or process optimization. The first type of machine learning technique that we're going to go into first is supervised learning, and we're going to do this through some toy problems. And this is where we have data that comes along with labels that we're trying to predict. So in this toy problem, we're trying to create a program that recognizes coins, such as in a vending machine. And so we know that coins have a particular denomination, such as a quarter or a penny, but they don't all have the same weight or size within the same category. They might have been manufactured at different times or in different places, or they might have different levels of wear and tear. So in this case, you don't want to program this explicitly because of these different variations. Instead, you might want to train a machine learning algorithm in order to solve this issue. So to do this in the machine learning area, you first assemble a bunch of coins. You would note their sizes, their weights, and their denominations. And if you were to plot that on the graph, it would look like the one on the left. So now to train a machine learning model to figure out their different denominations, essentially what you're trying to do is you're trying to draw these lines in between the separate denomination, like how it's shown on the right. This is a classic example of a supervised learning problem. Here we're providing the inputs, which would be the weight of each coin and its size, as well as what the correct output would be, which would be the denomination. And the algorithm tries to figure out how to predict the output given these inputs. In machine learning, these inputs are called features, and the output is called the label. And so we're going to see a couple more examples of this in the next few slides. Here we see a more realistic supervised learning problem that you might see. So in this use case, we have a clinical researcher that is trying to use historical patient data in order to create a predictive model that can identify if a patient has hyperthyroidism. So the table here you can see represents the historical data that they've collected. The columns on the left are the features or the inputs to the model, as we've learned. This may be different patient attributes or different properties of the patients that were collected at a clinic. And the label on the right is what we're trying to output from the model or what we're trying to predict. And this is whether the patient has hyperthyroidism or not. This is, again, an example of a supervised learning problem because the algorithm is working under our supervision, per se. We've provided with the correct answers. More specifically, within the supervised learning realm, this is an example of a classification problem because we're trying to classify the inputs into various categories. The categories in this case being hyperthyroidism or not. Quickly, we're just going to go through one more example of supervised learning. Here, a data scientist is using historical data to predict the taxi fare that you'll be charged in New York City depending on different pickup times and different routes. So again, the features here are the columns that are on the left, and this includes different characteristics of the past trips that we've collected, like the pickup times or the pickup and drop-off locations. And then the label, which is what the model is trying to predict, is the taxi fare that was charged. And unlike the previous use case, the model here is trying to predict a continuous value, which is the taxi fare, unlike trying to classify something into a different category like the previous example. So for historical reasons, models like this that are trying to predict a continuous value are called regression models. Now that we've dove a little bit deeper into supervised learning, we're going to go into the next technique in machine learning, which is unsupervised learning, where we have the data, but we don't have an associated label with it. So we're going to go back to the previous coin example that we started with, and we'll ask the question, what would you do if you just had a bunch of coins, but you couldn't actually read the denominations on the coins? So in this case, we have some input data, which is the size and the weight of the coin, but you don't actually have an associated output with it. And that's okay because we can still learn something from this data. For example, what if we try to group them together based on some shared characteristics? Maybe we want to put all the heavy and large coins into one grouping, and we want to put all the small and light coins into another. And in fact, this is a type of analysis called clustering analysis, and it's a very commonly used in a lot of different industries. And there are a number of machine learning algorithms that can do this type of analysis where they try to figure out some underlying pattern in the data without any supervision or labels, kind of not being told what the right answer is. And these algorithms are called unsupervised algorithms. And unsupervised learning has become very important in recent years, especially in NLP, where we are now training these large-scale models on huge corpuses of text. And then we can then use these models downstream for other types of tasks. And without having to have labels on our data in order to learn something, it becomes very powerful because unlabeled data is a lot easier to obtain rather than labeled data. Now that we've learned a little bit more about unsupervised learning, we can look at a more practical use case of it. So as mentioned on the previous slide, one of the most common use cases of unsupervised learning is trying to identify these natural clusters within our data. Customer segmentation is a classic example of this clustering analysis. So here's a simple example shown on the screen where a clustering algorithm is given data about customers, and it's able to automatically segment them into different categories. Now, the algorithm wouldn't be given those category names like student or executive that are seen on the right. That only happens that once the algorithm identifies these clusters, the human can go in and look at the clusters and be able to associate them with different groupings of categories. And in fact, a general rule with unsupervised learning is that a lot of times the output produced by these algorithms kind of requires some additional human evaluation to identify what the algorithm is actually learning. We're going to look at one last use case or practical example of unsupervised learning. Fraud detection is another common use case for unsupervised learning, and here the algorithm is trying to look at the data, trying to see if there's any instances or examples in the data that stand out as outliers. So if we take an example, we have a credit card and it's being commonly used for grocery store purchases, and then all of a sudden it's used at a high-end department store in a completely different city. Then hopefully those transactions in the completely different high-end department store should be flagged as an outlier by our algorithm. And this is because it potentially could be some credit card fraud that's happening. So we can look at this another way. In a way, you can think of outlier detection as the inverse of clustering analysis. And the cool part is we can actually use clustering analysis in order to identify outliers. So using our previous example, you can first identify the natural clusters within the credit card data, and then we would see, hey, which of these instances or example in the data don't fall into any of these clusters, and those would be your outliers, which could be fraudulent. And like with customer segmentation, a lot of times with these fraud detection algorithms, it typically involves some sort of human review at the end to go and figure out what the algorithm is actually learning. And there's one cool advantage of using these unsupervised anomaly detection algorithms is that inherently they allow you to detect anomalies that you've never seen before. Then this is because all the algorithm is doing is trying to learn what does normal data look like, and if it sees something that doesn't fit into what it seems is normal, it'll tag something as an anomaly, even if that anomaly has never been seen before. So now that we've learned a little bit about supervised and unsupervised learning, we're going to go a little bit into the last type of machine learning, which is reinforcement learning. You've probably seen this in the news with things like AlphaGo, where it learned to play the game of Go, or where it tried to learn how to play StarCraft. And so this is a lot closer to how humans actually learn by trial and error. So to try and describe how reinforcement learning works, we can consider an algorithm here that's trying to learn backgammon. So the input to the algorithm at each step is the current state of the board. So what does the board look like? And you roll a dice and you have to decide what pieces to move. And each of these moves will correspond to a different output state. And the move is considered to be an action in reinforcement learning. So now the algorithm needs to decide how good each of these moves are. And it does this by playing the game millions or billions of times. And then internally, it learns the internal mechanisms to tell it what's a good move and what's a bad move. And it does this by being rewarded by succeeding. So for example, in backgammon, it might be rewarded by winning the game. And so eventually, after playing the game many, many times, it'll learn how to actually act to succeed in backgammon. So playing games like backgammon or StarCraft or Go are cool and all, but reinforcement learning also has practical use cases in the industry. So one example would be robotics, where we can enable robots to learn by interacting with a simulated environment how to accomplish a task. Because this might be a reinforcement learning agent learning how to grasp different objects or to sort different objects. And you train this robot through a sequence of decisions that it has to make, and it receives reward, positive or negative, based on the decision that it makes. And so you can teach these robots to do a sequence of tasks that need to be achieved. Quickly, before we moved on from this section of the talk, I just wanted to quickly stack on Ensemble Models, which is more of a classic machine learning technique where you use multiple learning algorithms to actually obtain better predictive performance. So this is to overcome some of these technical challenges such as high variance where the model is very sensitive to different inputs, or it's not very accurate, or there's a lot of different noises and biases within the features. And so what you can actually do is you can train a bunch of different models, and then you can combine their decisions into one model in order to get a better model. So I just wanted to quickly point out that's a classic way where you can actually combine a bunch of these models together to get better predictions. Now that we've learned a lot more about machine learning and the types of problems that we can solve with machine learning, I wanted to dive a little bit more deeper into deep learning. Before we learn about deep learning, I wanted to set the stage for why all of a sudden are we seeing deep learning being used across all these industries, and why is it having all of this success now? First, let's go through a very basic introduction to the mechanics of a neural network and how it works. We'll go deeper into the process of developing a deep learning application later. You can see here on the left a depiction of the base unit of a neural network, which is a neuron. It takes in a vector of numbers as input and multiplies this input by a set of weights and then adds a bias vector. And at the end, applies a nonlinear activation function such as a sigmoid. In deep learning, we stack layers of neurons together to create a network by feeding the output of previous layers into the next layer, which we can then use to make a prediction. This stacking of neurons allows it to create more complex and complex logic that it can learn internally. We can then train it on a data set with a method called gradient descent and backpropagation to adjust the weights so they give the desired output given an input. For example, as we'll see a little later, we may train it on a data set of cats and dogs to output dog or cat given a respective picture of a cat or a dog. What may surprise you is actually neural networks are not new. They were first theorized in the 40s, first implemented in the 50s. Backprop was first used in the 80s. And it's pretty simple comparatively to a lot of alternative machine learning algorithms. So the question is then, why did it not work in the past and why does it work now? And we'll see this in a little bit. So if neural networks have been around for a really long time, why haven't we been using them for a while? And this is because neural networks historically performed very poorly comparatively to other alternative machine learning algorithms, such as support vector machines. So historically, a support vector machine would work a lot better on trying to predict on the data or learn from the data, so there was no point in using these neural networks. And why did these neural networks underperform? It's because there just wasn't enough data and they weren't being used with enough data. And so the more training that you provide to these algorithms, the better accuracy you're going to get. And it's also, the problem is that increasing the amount of training data only improves the accuracy asymptotically. So for the amount of data to move up a couple percentages early on, it takes an exponential amount of data in order to get that same accuracy improvement later on. And so you need an exponential amount of data in order to train to get increases in performance. So what's been done in the past historically to overcome this property of machine learning algorithms where there's this exponential hunger for data in order to improve the accuracy of the model is we'd work on new algorithm development, or more importantly, what usually is done is feature engineering. So for the last couple decades, what data scientists in most of the AI fields have been doing has been investing huge amounts of effort to develop new methods for representing their data to make the problem easier for machine learning algorithms. So effectively what they were doing is they were injecting their own human knowledge into the problem to make it easier for the algorithm. So as we saw earlier, each neuron takes in an input and calculates its weights and biases, but it becomes a much easier problem if you can engineer the original input into this model in order to be an easier problem to solve. So as they did that, they systematically managed to move this curve upwards. And this is a lot of times the foundation of a lot of different machine learning research and how machine learning algorithms are actually developed in the field. Here we can see that the neural network that didn't take advantage of the manually engineered features by the data scientist, or maybe only took advantage of it to a limited extent, performed very badly in comparison. We'll see there's a couple different reasons for this behavior. So in the past, we never had these large-scale data sets that deep learning needs. The concept of big data and scaling data sets wasn't in our history. And that's largely because we never had the internet in order to collect these large data sets. So in the picture on the left, that was what represented the state-of-the-art data set used in vision research in the 1990s. It's just 60,000 handwritten digits that are black and white and only 24 by 24 pixels. Second reason, besides these large data sets that are needed for neural networks, we also needed substantially more computational capability in order to train these neural networks on these larger data sets, which was also a hindrance in order to train these networks to perform better than classic machine learning. Luckily, as the large data problem has been able to be overcome in recent years with these larger and larger data sets that are being collected, also compute for the last several decades has benefited from an almost exponential increase in computational performance. So with these larger data sets that we're now collecting, we're getting larger and larger computational capabilities, and now with the GPU and its massive parallelization of these neural networks that allow us to do many computations at the same time, we can scale up our compute with our larger data sets, which allows these deep learning algorithms to perform even better. Just to kind of quickly summarize what's happening and the reason for these neural networks is now that we have the large data sets that are required for deep learning, now that we have the computational capabilities that are required to train them, and now that we have some of these new techniques such as batch normalization, which we haven't gone over, but it has made training these large neural networks a lot easier, making them possible. Where before 2015 to 2016, training these large neural networks was basically impossible. And in this case, size does matter, where the larger the neural network you create with more complexity, with larger data sets, usually these neural networks are just becoming more and more accurate. And so we're seeing now that to tackle a lot of these increasingly challenging and complex problems, what is happening is these neural networks are scaling up and they're getting larger and larger data sets, allowing us to accomplish more and more complex tasks. We've just learned the basics of what a neural network is. It's a stack of these basic functions called neurons into deep networks that we then use to train to make predictions. We found out the reason that they were not successful in the past was their historical inability to scale to the needed size in order to be able to be effective. I want to now go a little bit more deeper into the process of how deep learning works when we're trying to use it to solve a specific problem. So now we're taking a look at deep learning application development in the real world. How does it actually work in practice? So we're going to start with a sort of toy example. So say you want to identify automatically with deep learning various types of animals, which is a classification task, as we've learned. So the first step would be to assemble a collection of representative examples that are going to be used in our training data set, which will serve as the experience or what our deep neural network is going to try to learn from. So say, to simplify it down, we're only needing to classify between cats versus dogs. Then realistically, you'd only need to have images of cats and dogs in our training data set. So to give an example of scale, in this small example, you probably only need several thousand images, each with a label indicating whether it's a cat image or a dog image. And to ensure that the training set is representative of all the pictures of cats and dogs in the world, it's probably going to include a wide range of different species, kind of the dogs and cats in different poses and environments in which the dogs may be observed, so that it can be representative of, or just be a sample representative of what all the dogs and cats might look like. So the second step in deep learning application development is we need to get an untrained deep neural network model. So as we've seen, deep neural networks essentially are just a set of these neurons that take in input, multiply them by a set of weights or numbers, add a set of numbers called biases, and then run them through a nonlinear activation function, as it's called. And then you just stack these together in layers and you have deep neural networks. So as we can see here, we have this neural network on the left. And usually neural networks are designed to perform a general task, such as detection, where you try to detect an object within an image and where it is. Classification, like we're doing right now, where we're just trying to say, hey, what's in this image, a dog or a cat? You also have tasks such as segmentation, where you're trying to classify each pixel in an image to be a certain class. So you might say each pixel is a dog pixel, a cat pixel, or neither of them. And so each of these neural networks is also designed to take in a specific type of input data, such as an image in our case, or they can also take in text, audio, or video. So here on the left, you can see a very simple model of an untrained neural network. This is just to represent what a simple neural network looks like. So at the top of the model, there is a row or a layer, as it's referred to, that has 4 input nodes. And at the bottom, there's a layer that has 2 output nodes. So between the input layer and the output layer, all of these layers are referred to as hidden layers. That is too important right now. The white lines show which nodes in the input layer share the results with the nodes in the first hidden layer, and so on all the way down to the output layer. And so you may refer to these nodes as perceptrons as well. We've also seen as they're called artificial neurons. And the reason why these are called this is because simply their behavior is inspired originally by the design of the neurons in the human brain. Now, this is a really simple view you can see here. A real deep neural network model would have tons of many hidden layers between each of the input layers, where they're passing the output of the previous layer to the next layer, where it does the multiply by the weights, add the biases, and do the nonlinear activation function. And this is where we get the term deep in deep learning. This is super simplified, as I've already said, but we're just going to keep it here as an example. Now, I just want you to keep in mind that the design of all these neural network models are what make it suitable for a particular task. So There's different models will work better for tasks like image classification can sometimes be pretty different from the best model for speech recognitions. And these differences include the number of layers, the number of nodes in each layer, how the algorithm is actually performed on each node, and the connections between the nodes. We're going for a very high level overview in this talk. So it's also worth noting that there are readily available deep neural network models for all of these tasks for image classification, object recognition, and image segmentation that have already been proven to work very well on these tasks. So it's not necessarily to go and modify these models specifically for your task to achieve these high level accuracy. They're already out there. You can take them off the shelf and then use them on your training data set in order to, say, classify dog versus cat. So now that we have our training data set, which is made up of cats and dogs and the labels that are associated with each image of whether there's a cat or a dog in the image, and we also have an untrained neural network that is designed for our specific task, in this case classification, trying to classify is there a dog, is there a cat in the image. The next step is actually to train the neural network to be able to predict whether there's a cat or a dog in the image. So what you do is you take a deep learning framework such as MXNet, PyTorch, or TensorFlow in order to feed the training data set through the neural network. The deep learning frameworks really aren't as important for the most part. They have their own strengths and weaknesses, but for the most part, any of them can be used. So for each image that is processed through the neural network, each node in the output layer, the last layer, reports a number that indicates how confident is it that the image is a cat or a dog. In this case, there are only two options, so the model needs just two nodes in the output layer, one for cats and one for dogs. If you have more categories, you just have the same amount of output nodes. And so when these final outputs are sorted most confident to least confident, the result is then called a confidence vector. The deep learning framework then looks at the label that you've provided for the image to determine whether the neural network guessed, which in the terms of neural networks, guessing is also called inferring or inferred the correct answer. If it inferred correctly, the framework strengthens the weights of the connections that contribute to getting the correct answer, and vice versa. So let's say your neural network inferred the incorrect results, the framework then reduces the weights of the connections that contribute to getting the wrong answer. And this is how you train a network. It's called backpropagation. We won't go too much into the actual mechanics of training the neural network with gradient descent and backpropagation, but you can look that up on your own. And then after processing the entire training data set once, the neural network will generally have enough experience to kind of infer the correct answer a little bit more than half the time or slightly better than random. So it'll require several additional rounds of processing the entire data set. Processing the entire data set once is referred to as an epoch to achieve these higher levels of accuracy. So you keep feeding the training data set through the network as it's guessing, and the learning algorithm is telling it to adjust the internal weights of the network for how to do better in the future. So now that the model has been trained on a large representative data set for long enough, it should be pretty good at distinguishing between cats and dogs. But if you showed it a picture of a raccoon, for example, it would be very confused and says no previous experience with raccoons. So if it hasn't seen something before, it's going to get really confused, and it would probably report a pretty low confidence score for cats and dogs, and it would just probably be outputting random stuff. So if you need to be able to classify, say, raccoons as well as dogs and cats, you need to modify the model to add a third layer node to the output layer, to retrain again with a new data set that also includes a bunch of different images of raccoons, and retrain it so that it'll be able to identify raccoons, dogs, and cats. Cool thing is there's no need to manually write a raccoon feature extraction algorithm to figure out how to integrate it into your deep neural network. You just modify the network a bit and then you can retrain it, because the network is learning on its own how to do this feature engineering, or how to learn what does a raccoon versus a cat versus a dog look like. So now we have our model. It's been trained to distinguish between cats and dogs. And usually at this point, what you would do is you'd optimize the model to run significantly faster at runtime. So when it's doing its inference or trying to predict whether a cat or dog, you can do it a lot faster, because a lot of the flexibility that was necessary during training is no longer needed. Now, one thing I wanted to point out right now that I had simplified over in the process is the untrained neural network model. Typically nowadays, what we do is we do a process called fine tuning, where instead of just taking a random untrained neural network model, what you do is you take a pre-trained network that's been trained on a very large amount of data. Say it's been trained on millions and millions of images and it's had to predict many different categories, and we take that model and we try to fine-tune it on our data set of trying to detect cats and dogs. So we try to take these pre-trained weights that we have and try to detect cats and dogs with it. And the idea with this is usually it requires a lot less data on our side to be able to predict cats or dogs, because the internal features that this pre-trained network has learned allow it to be able to more easily already be able to recognize dogs versus cats. But I'm not going to go too deeply into that process. So now that we have our trained model that's fully trained, optimized, and is ready to be integrated in the application, this is called the inference stage, and this is where it'll be integrated into your application. It'll fed new data, and hopefully in this case, images of cats and dogs it hasn't seen before. It'll be able to quickly and accurately infer the correct answer based on its training. There's a bunch of different ways that you can add these into your application, but hopefully now, depending on what the task that the neural network is trying to accomplish, it can do. And you might have to go back to earlier stages where you collect new data as you're doing inference, and you can retrain models and keep this process iteratively going in order to improve your model. Now that we've learned the basics of deep learning, the types of problems that we can solve with deep learning, and kind of the process of going through and collecting and training these networks in order to make predictions, we're going to hone in a little bit more on specifically the types of problems in your guys' areas that we can go about solving with deep learning. Often when you're trying to figure out whether deep learning can be used to solve a specific problem in your business, or you're just trying to figure out what problems can be solved with deep learning, it can be helpful to think about it as a way to map samples from an input domain to an output domain. So an input domain can be almost anything. It can be text data such as log files or financial data. It could be images of pretty much anything, audio or other signals or video streams. It can even be three-dimensional images such as those captured through geophysical analyses or cosmological models. Then you need to figure out where your output domain is. And so the output domain is determined by the question you want to ask of the input data. And the question itself indicates the type of deep learning task you need to perform in order to map this input domain to the output domain. So we can see on the right, we have this table that kind of defines what type of task we're trying to figure out. So a business question could be, is it present or not within, say, an image being the input? The task would then be detection, and in a use case between the oil and gas industry could be anomaly detection, where you're trying to, from images, kind of figure out where there might be some anomalies that might have something go wrong. Another example would be, what is the most likely outcome? So you might be trying to predict failure of certain equipment. And so there's a bunch of different ways where you can frame your problems, and then you can be able to figure out what the deep learning task is and the type of model that you're trying to use is. The energy customers span a wide spectrum from upstream to power distribution. In upstream, we focus on everything from seismic imaging and interpretation to reservoir simulation to predictive maintenance, health, safety, environmental, and monitoring and surveillance. This requires significant compute power, however, also requires visualization capabilities and AI ML implementation. In midstream, we focus on everything from AR, VR for logistics and training, to pipeline integrity, to HSC and intrusion detection. We require the same hardware and software capabilities as for upstream. We also focus in downstream, which includes power plant facilities and predictive maintenance, along with gas stations and customer service. Finally, power generation and distribution is one of the newer sectors we've been working in. We aim to simulate load requirements for optimization, along with plant and seasonal operations optimization. This all requires data management and remote monitoring. There are a wide range of functions these customers fulfill that combine scientific simulation, visualization, data analysis, logistics, etc. The volume of machinery and equipment that is deployed to support all these functions is huge and needs constant monitoring because malfunctions can be catastrophic for Earth's ecosystem and human life. Being a mature industry, it relies heavily on technological innovation to improve efficiency, safety, and cost reduction. Using the underlying technology used, one can find the commonality along all the functions. For the next few slides, I'm going to be going through some of the common deep learning architectures and how they can be used and applied across the petroleum industry. The first deep learning architecture that I'm going to go through is convolutional neural networks, which are used in computer vision tasks. So at a high level, convolutional neural networks have these small little kernels or filters, and they are striated along an image to extract features. And the neural network is able to learn the weights within these small little kernels in order to extract features locally from our image. And we stack these together in a deep learning fashion and send them through large multi-layer perceptrons in order to extract features. And these types of networks are really good at any sort of computer vision task. This could be anything from detection, where we're trying to detect where an object is in an image, or for classification, just to say what is this image representing, what class is it. Pretty much from any sort of computer vision task, convolutional neural networks are a great way to go. A great example in the upstream world of applying these convolutional neural networks, or CNNs as they're referred to, on video and image analytics is detecting occupational health and safety issues. We're seeing several operating companies are now deploying video cameras, drones, and body cams across the production facilities or drilling rigs to alert on probable safety issues. This is including missing personal safety gear, social distancing, or any of these other kinds of near misses. Another great example of applying CNN networks is to do mechanical integrity inspections to detect any corrosion-related issues, pipe leaks, ruptures, or any loss of primary containment. This is just a few. There are hundreds of other use cases using CNNs, which are now allowing oil and gas companies to avoid sending people on the site for plant walkdown and use AI to capture possible incidents more accurately and proactively. CNNs and other deep learning computer vision models' flexibility allows them to be applied to a wide range of problems that require taking images as the input and making predictions or classifications. The next deep learning architecture that we're just going to quickly go over is for sequence modeling. This is where you might have your input data being a sequence of features. The type of model that's commonly used here is called a recurrent neural network. It's where a recurrent neural network has a special property where it has an internal representation that is kept from sequence to sequence. So you feed it in data, it might make a prediction. It moves on to the next time step or next part of the sequential data. It takes that as input, but it still remembers the previous input so that it can learn from sequences in order to output some of these models. So this can be anything from time series data to languages commonly used. And it's a great way to model anything that you require this sequential nature to remember previous things. So we've just gotten a high-level overview of RNNs, or recurrent neural networks. And recurrent neural networks work really great when your input data is in the form of a sequence. So a great example of an RNN network is to do predictive maintenance analytics. Turbine or a gas compressor might have more than 3,000 plus different pieces of components, and process upsets happening in the upstream and downstream of the equipment can cause failure in any of the components. Using time series data coming from sensors such as temperature, pressure, or vibration, RNNs can identify anomalies from the process data early enough, which may lead to possible equipment failure. Companies are applying the same method to detect failures in the artificial lift equipment such as ESP and rod lift to calculate the end of remaining useful life. But these RNNs can be pretty much applied anywhere where you might have sequence data and are pretty useful when trying to do any sort of anomaly detection or predictive maintenance. The next deep learning architecture they're going to take a look at is transformer networks that are used in language modeling. This is probably the most advanced network that we're going to take a look at, so we're really not going to go anywhere deep into it. But the idea is these language models have these layers called attention networks, where they are able to attend to different parts in the input sequence, which makes it a great use case for trying to model the relationships within language. That's pretty much all you need to know at a high level. And they take these language models, these transformer networks, and they train them on super large corpuses of text, where they have all of, say, Wikipedia they've trained on in order to try and learn the semantics and how language works. Then you take these large models and can use them to apply to different downstream tasks, such as trying to do sentiment classification or trying to build these chatbots or conversational artificial intelligence. So they've been able to distill all of the semantics and knowledge of language down into these large models, and they work fairly well in any of these downstream NLP tasks. So downstream, these large transformer models can be applied anywhere where you might have language involved. So you can apply these NLP models to create engineering, maintenance, and operational chatbots using engineering documents, operational manuals, and other operational documents. So you would take these large transformer models that have already been trained on large corpuses of text, you'd then train them a little bit on these engineering documents, and then you would be able to use these models in order to make chatbots that would be able to answer any questions on any of these manuals or maintenance documents. Here we're just going to take a quick look at a more advanced type of model class called generative models. So previously we've been working with only discriminative models, and these are models that try to discriminate between different kinds of data. But a generative model tries to actually generate new data instances. So one that we're going to look at right now is called an autoencoder. And so autoencoders are a form of unsupervised learning, which means they don't have to have a label associated with them. So an autoencoder consists of two parts. You have the encoder and the decoder. So it takes as input your data sample, it passes it through the encoder to a bottlenecked area. So this is a compressed layer. So all it can do is try to retain the important information. And then the decoder part of the neural network tries to map it back to the original input. And you train the neural network by trying to minimize the reconstruction error, trying to make it so that what was input gets output again and generated. Now, an interesting part of this is that now the most important information from the input space of your data set, so it could be anything from time series data to images, is now bottlenecked into this bottlenecked area. And so an interesting property of this is that you can actually use it for anomaly detection, because now if you go and put something that it is not like the other images where it hasn't been able to be compressed in the same way into this bottleneck like other previous inputs, it's going to have trouble being reconstructed when it passes it through the autoencoder. So this is an interesting way to do unsupervised learning anomaly detection. Another class of generative models that we're going to take a quick look at are called generative adversarial networks, or as they're referred to as GANs, and these have been making a lot of progress in recent years. If you've ever seen the faces in the news where someone tells you, hey, these faces were generated by an AI, they're not actually a real person, but they look just like a real person, then it was probably from a GAN. And so a generative model is just trying to generate samples that have the same characteristics as the samples that are in the original data set. And it does this in a pretty clever way where you have two networks now. You have a generator that's trying to produce fake samples, just like from the ones in your data set, and a discriminator that is getting samples from both the generator and the data set, and it's just trying to tell, hey, is this a fake sample or a real sample that actually came from the data set? So during training, all you're doing is alternating by training the generator to produce fake samples that fool the discriminator, and then also training the discriminator to be able to recognize between real samples from your data set and those from the generator. And eventually, if you train this long enough, the generator will actually get really good at generating samples that look just like your real data set that you started with. We just learned how autoencoders can be used for doing anomaly detection, because when a sample is passed through, the reconstruction error is going to be really high for these anomalies. We can also use GANs as a way to do anomaly detection as well, where we can take the discriminator and use that to decide what is anomalous and what's not. Now, these generative models also have a very powerful use case, which is for generating synthetic data. And so you can use these models that have learned a distribution to generate new samples that you've never seen before. And you can use these GANs to do simulation data for employee training or places where limited data is available. They can also generate missing data or replace incorrect data. And missing and lack of data are some of the biggest hindrances in data science. This is usually what takes some of the most time. Sometimes 70 to 80% of the time is during this data preparation stage. And oil and gas have tens of thousands of real-time sensors, IoT devices generating data all the time, and the malfunctions in the instrumentations, the communication failures, and the lack of failure history are some of the major issues where the industry could just use these GANs to generate synthetic missing data. So it's one of the most powerful tools that AI has been able to produce in a while. Now that we've gone through some specific types of deep learning and machine learning models to see where and how they can be applied in the industry, I want to take some time to talk about some of the more specific cases where deep learning is being applied now in the oil and gas industry, and some kind of case studies to go over. First, you can learn a lot from microfossils deep inside the Earth, such as the age, thermal maturity, and paleoenvironments of sedimentary strata. That's why the oil and gas companies like Total have been using micro CT scans of samples for years. The biggest problem with this is that a single 3D micro CT scan can have over 800 microfossils, and each need to be properly labeled and identified for analysis. This typically takes a single geologist an entire month to work through. That's why Total partnered up with InstaDeep to build an AI-powered toolkit to automatically label microfossils in a fraction of the time. This is challenging for several reasons. First, when you're working with 3D volumes, there's a lot more data and it's a lot more difficult than in 2D images, which is part of the problem why it's so hard to label in the first place by a human. The second is that Total needed more than just segmentation or dividing microfossils from non-microfossils. They needed instant segmentation. The difference between instant segmentation and semantic segmentation is in one, you just want to label every part as what is its class, but instant segmentation, you need to be able to individually identify each entity, which is a much harder problem, especially in deep learning. Third, they need to build a volumetric data pipeline capable of inferencing huge amounts of data. So even with deep learning, this is a super difficult problem, but it would save a lot of time for the downstream task if you were able to automatically identify each instance within these scans. In order to kind of describe the process that they had to go through when trying to build these deep learning models, I'm going to go a little bit more into the specifics, and it's a little bit more advanced than if you were a simpler user, but it's nice just to have an idea of what it takes to kind of build these models out from the ground up. So they started out with a layered 2D mask or CNN approach. This was sufficient for just doing image segmentation of 2D slices, but led to a lot of discontinuities in 3D volumes. And the model suffered a lot from not having enough data to be able to train well. So next, they tried semantic segmentation using 3D UNet. And this had pretty good segmentation results, and 3D nature solved the discontinuities, but it still lacked the ability of doing instant segmentation, which didn't meet Total's needs. And the model was, again, suffering from not having enough labeled training data. So we've seen some of the process as InstaDeep is slowly eliminating different problems within their deep learning models. So what was the final use case? Finally, InstaDeep turned to the medical community with a 3D mask RCNN model that was originally developed by the German Cancer Research Center. And this is a point that we talked about earlier, where a lot of these models that are used to solve problems in different areas will work well in a completely different industry. So you don't actually have to start from square one. The model required some work to make it applicable to this use case. The medical model had different resolution for the z-axis compared to the x and y. So first they had to refactor it to be isotropic. Next, they had to take the model that was originally designed for a single GPU and then distribute it across multiple GPUs, which again is no easy task. And this all resulted in a model that quickly and accurately detects, localizes, and segments individual microfossil entities in 3D. By performing segmentation after detection, InstaDeep was able to eliminate false artifacts from being created. The data pipeline was optimized to better utilize small amounts of training data, so it didn't have to have as large of a data set, and infer on massive amounts of new data a lot quicker. It's also robust enough to handle various input shapes and sizes for training and inference. Along the way, InstaDeep implemented several innovations to make the model work. They took the 3D model originally designed for the medical data. They refactored it as isotropic, as we just said. They trained it on geological data. They designed and implemented a smart data pipeline optimized for volumetric datasets. Then they were able to train on large, complex models on small datasets while running inference on much larger ones. And then finally, they were able to scale up the model and distribute it across multiple GPUs. This required 5 separate modules, a ResNet 101, and a feature pyramid network, a region proposal network, a classifier module, a mask network, and loss computations. And we've talked about all of these kind of components already today. These are just more specific examples of some of the networks that you might use or what some of the data pipeline might be. And the model, surprisingly, was able to generalize very well. And although a lot of what was just talked about was complicated, I think the important takeaway here is that it was able to massively reduce the amount of time it took to label these CT scans, all by taking inspiration from deep learning in the medical space. Now we're going to take another look at another different case study for optimized well placement using deep learning. One of the greatest challenges for the upstream oil and gas sector is the optimization of well placement in oil and gas reservoirs. To give a sense of the scope of the challenge, a game of chess has nearly 5 million possible moves after just the first 5. Now optimizing well placement in a small reservoir can have as many as 10 to the 14th or 100 trillion possible combinations within only 5 sequential, non-commutative choices of vertical well drilling location. So it's a ton exponential growth. The objective is to maximize productivity and profitability over the projected lifetime of the hydrocarbon asset. And this problem quickly becomes computationally unmanageable without the adoption of cutting-edge AI frameworks and HPC workflows, especially when critical decision-making is impacted by other areas of uncertainty. So usually reservoir grids often have fine resolutions containing hundreds of wells within different trajectories and can be simulated over the course of decades, encompassing thousands of possible well decision steps. Experts in this area have been tackling this in a non-deterministic polynomial time hardness problem with a combination of brute force and other optimizations, such as particle swarm and genetic algorithms. Applied this already on top of a very computationally expensive reservoir simulation, and this takes tons of time. So as you can see, this is an extremely difficult problem, but you can see that even with a small improvement, you can lead to massive gains in profits. So we'll now take a look at how Beyond Limits was able to use a reinforcement learning agent in order to solve this problem. As we mentioned earlier within the talk, when you have a sequential decision-making process, this is a framework that reinforcement learning often has a natural fit, and that's what Beyond Limits did with optimized well placement here. So Beyond Limits took the novel reinforcement learning framework based on advanced soft actor critic paradigm and applied it to the sequential decision-making problem of well placement and trajectory design in field planning optimization. The specific benchmark problem that was used was the egg reservoir model, which has mathematical relevance and widespread use in the optimization field. It was initially adopted as a test case for the framework to begin. So the optimization objective included maximizing net present value, or NPV, the projected dollar value of extracted hydrocarbons for a given field with a specified number of producer and injector wells. A greater number of wells results in both higher drilling costs and increased risk of negative environmental impact. Therefore, maximizing returns while minimizing the drilling is what is most important. The computational resource utilization of the reinforcement learning framework and dynamic reservoir simulation were both monitored for benchmarking. The advantages of this fine-grained parallel computing and reduced resource contention made it possible by the platform were quantified using key metrics. These include the best NPV obtained, the number of action explorations, and progress in the episodic reinforcement learning for a fixed time frame. The results were then compared with runs performed by the other optimization paradigms to see how well it performed. So Beyond Limits accelerated reinforcement learning solution optimized for well decisions by identifying several thousand combinations reduced from the 100 trillion that we mentioned earlier of possible combinations to yield near optimal results in a typical reservoir. Small enhancements achieved by solving at this speed and scale reduce well placement in a typical reservoir from months to hours and yield millions of dollars in additional value. The reinforcement learning algorithm is designed to explore solutions working in tandem with these deep convolutional neural networks that predict both the action to take and the value of the specific state. These solutions are collections of well trajectories and drilling cues that maximize profitability while reducing the environmental impact along the way. And by performing spatial temporal optimization, the number of wells need to be drilled to extract a desired NPV worth of hydrocarbons is minimized while the NPV itself is maximized. The adoption of HPC accelerated AI workflows represents both the vision and the objective for the upstream oil and gas industry. More importantly, the framework developed by Beyond Limits will continue to grow in leaps and bounds within this space, and its applications have use cases across the downstream sector, power utility grid management, as well in the medical and healthcare field. So they were able to take these paradigms in deep learning and able to cut down their time almost by a magnitude. One last specific example that I want to touch on very quickly was work that was done with Blueware. Interpreting seismic data is a long and painful manual process that can add months to seismic processing timelines, and it typically requires a team of geologists and geophysicists weeks to months of manually picking fault lines, various horizons, and salt body boundaries. By leveraging the power of computer vision, we can train an AI model to automatically interpret seismic data, identifying nearly all of the geological features that a human eye can. That's exactly what Blueware does with their interactive AI solution. They take a unique approach to model building by training a model while a geologist labels the data, greatly reducing the project timeline and time to value. So a lot of these common computer vision cases can apply directly to the industry and are pretty easy to get going very quickly by just taking models that are off the shelf. And the best part is that after you use the solution, you can iteratively improve on it as you get more data, and the solution will just get better and better. We're now getting to the end of the talk, and hopefully by now you've gotten a broad overview about what is machine learning, deep learning, and then hopefully how you can apply it to your own problems and where it fits into the big picture with petroleum engineering and these specific use cases. And we're now going to go into a little bit about how you can get started. So where you can get your feet wet, maybe some good courses to get started with, and where you can learn more about using deep learning and applying machine learning to your types of problems. The first resource that I would recommend if you wanted to get a little bit hands-on in learning about deep learning would be the Deep Learning Institute, and this is from NVIDIA. And this is where you provide the fundamentals and some hands-on training in trying to get started with deep learning. So this will cover all different types of areas. We have the fundamentals of deep learning where you can get just the basic overview and technically hands-on with Jupyter notebooks in how to work with deep learning, all the way to specifics such as in NLP, conversational AI, or computer vision. You can take a lot of these in self-paced courses or with certified instructors from NVIDIA and across different ambassadors that will be able to teach you live in class about these different areas. So I would definitely recommend this as one of the first places to go check out and see if there's some courses that might interest you. Another great resource for learning a lot more about deep learning and machine learning are all the courses that are on Coursera. There's a lot of great courses, and this is where a lot of people classically have learned and gotten their feet wet in deep learning and machine learning. There's a lot of courses on here where you can learn the basics of neural networks and setting up data science projects. You also will learn more about the sequence models that we've quickly talked about today, convolutional models and transformer models. So this would be one of the best resources for trying to actually get your hands on and learning with the math behind machine learning and actually how to code with it. Here's just one last option if you wanted to try and get your hands on with some deep learning. I would definitely recommend the first two options. I have had hands-on experience with both of those, and those were great learning resources. But there's also a third course, the Practical Deep Learning for Coders from FastAI, which is another MOOC just like the Coursera one. It gives a broad introductory course for deep learning, similar to the Andrew Ng course. It has a book that goes along with it, and it teaches the basics of PyTorch. So this is another great resource if you want to get hands-on. Another great resource offered by NVIDIA is the NGC. This is not a course, but a place where you can pull convenient environments for development or production deployment. And it's a good place that provides optimized containers. So these are performance, they're updated monthly with Docker and Singularity. And it also provides pre-trained models. So this in popular applications or industry use cases. So if you want to see, hey, I just want to quickly test whether these pre-trained models, I can fine tune them on my own data. There's probably a model that will relate to a lot of your different problems. And you can just retrain on your data, and there should be an easy way to deploy it quickly. There's also a bunch of different types of model scripts. If there's a model that you've seen before, you can go into NGC and try and pull it, and it's all in Docker to be easy for you to play with and get hands-on with, and state-of-the-art across many different domains, whatever your popular framework is. And so it's a great way to try and pull these pre-built models and try and see, hey, quickly, will this work if I apply it to my problem in my area? So I'd also recommend taking a look at NGC. We now came to the end of the course. Just wanted to quickly go over the learning objectives that we hopefully got from this. Hopefully, at the end of this, at the beginning, we described the difference between artificial intelligence, machine learning, and deep learning. I hope now that you can see the different categories of supervised versus unsupervised versus reinforcement learning, and also be able to distinguish between statistical techniques classically, machine learning, graph analytics, and deep learning. And then also, we went through a little bit about how you can take a question and see if deep learning would be maybe a solution for you, and some of the applications that are already being used in the oil and gas industry. And then at the end, we went through hopefully how to get started so you can get hands-on and actually get using some of these tools. Thank you very much for attending the talk today. Feel free to reach out and contact any of us at our emails, and I'm sure we'll be happy to answer any of your questions or point you to more resources if you're interested.
Thanks, Peter.
Thank you very much.
We'll now move on to our Q&A portion to answer some of the audience's questions. All right, we're now going to transition into our Q&A section since we've got some time for questions. Before we do, I'd just like to quickly mention that SPE is also having another event upcoming on this Thursday, August 26th. This will be for their Petroleum Data-Driven Analytics technical section, and it will focus on the democratization of AI and the future of AI applications, so be sure to check that out. Okay, so our first question, could you describe an example of graph analytics in the oil and gas energy industry? And I'll open that up to our presenters. We have Peter, Naselli, and Essen.
Yeah, so this is Essen over here. So there are a couple of things which you can do with around the graph network. The first of the example is if you are trying to look into your plant network, how your equipments, how your processes are connected, and understanding not just the linear, but also the non-linear relationship between the equipment and processes. So the graph network immensely help. You can understand the correlations between them, the cause and effect, which is happening between the process upsets or an equipment, any failure may be happening, and how this is impacting in the downstream of that process. So there's a lot of applications in the oil and gas industry when you're trying to understand the overall interrelations between the different equipments and the processes.
Excellent. We have another question. Okay. How will the increase in neural network complexity affect the types of problems that petroleum engineers can work on?
I guess I could take this. As the kind of complexity of these algorithms improve, it just means that we're going to be able to solve more and more general problems within the industry. And so as we've been seeing, as we've been moving forward in time through the past few years and deep learning has been getting more and more powerful, it just means that the complexity of the problems we're going to be able to solve is a lot higher. For example, before, maybe a couple of years ago, a lot of times it was pretty difficult to be able to detect in an image if something's really occluded or it's tiny. But as we've been getting better and better performance, and we've been using these new models, we're a lot easier to be able to detect these tiny little artifacts or small objects within images or slices. I don't know if anybody else wants to comment on that.
No, that's good. I just got just on a housekeeping. I'm not sure if the people can hear us loud and clear. Just want to make sure.
Yeah, I think we're good.
Okay.
Great. Okay. Our next question here: what are the trade-offs between using CNNs versus RNNs in some of those industrial applications that we talked about? So, yeah, maybe Peter or Essen or Naselli, did you want to chime in on that one?
Yeah, I can talk about that a little bit. Those CNNs and RNNs are kind of fundamentally used for different use cases. So CNNs are convolutional neural networks, and that's usually used when your input data is of some kind of image. So if you're taking images or you're trying to take these 3D CT scans, and that's for that space is when you're just trying to solve it when it's structured images. Now, RNNs are usually used for sequence types of problems. So this is anywhere where you have some sort of time series data or there's any sort of idea of a sequence of inputs. And you can actually combine the two of them together. So let's say you had a sequence of images, then you could actually combine the CNN with the RNN to be able to solve the problem. But they kind of fundamentally solve two different types of problems based on what the type of input you have is.
Great. Let's see. Okay, this one is going back to our microfossils example. So would you be able to talk more about the refactoring and distribution over multiple GPUs? I know you mentioned 3D mask RCNN. Would you like to comment on that one?
Sorry, could you repeat the question? I kind of broke up there for a second.
Yeah, no worries. So in that microfossils example, can you talk more about the refactoring and distribution that you mentioned over the 3D mask RCNNs?
I don't know if Essen or them wants to comment. I didn't work on that project directly.
So this is a very specific question, Brent, and I think so there are two aspects to doing when you have a large cluster of image, and then from the compute requirement perspective, it's just not enough to do it in a single GPU. So that's where you need to go to the multi-GPU and in fact into multi-nodes or really large clusters, right? And this is where it goes a lot more detail, and we're happy to take this question offline because it goes a lot more technical details than I think it's intended for the audience. We can be happy to answer that later.
Sounds good. Okay, this next question is talking about HPC. So can you talk about some of the ways that HPC or high performance computing is being used in energy today, whether it's for discovery, exploration, management, anything like that?
Hi, this is Saeed Mubarak. I'm happy to take this one. As far as high performance computing within the energy industry, we've seen it in several different areas. The first one that we've majorly worked on within NVIDIA is within seismic interpretation. That's been our core business for about a decade, a little bit more. So that's the first major area where we use high performance computing. We're seeing more and more the use of HPC with reservoir simulation applications as we move forward to help optimize these softwares to be GPU enabled and accelerated. We also, within work that we've done with different AI and machine learning projects, have been using HPC to power those. So within every area, specifically to subsurface and specific to seismic and reservoir, we use high-performance computing. Additionally, I believe Essen can speak a little more to what we're doing within the surface facilities, within the surface portion of the energy industry in regards to implementing high-performance computing applications.
Yeah, sure. Thanks, Nifali. So I think there's a big convergence, right? A lot of where we're doing the process simulations. You're running extremely large models, and what it is, how as industry is really pushing towards what you're calling them as a digital twins, right? Where you can simulate and understand what is going to happen and then take actions accordingly. So to make really a true living in the digital twins, may that be in the subsurface or on the surface side, you need to do these high performance simulation and you need to do them fast. So rather than running them for hours and days, you want them to become much more faster. And that's where there's a convergence into the reduced order models where you are going towards low fidelity models. So that helps to, you may get a 90% accurate results, and from there you can take an action. So it's becoming more like a recommender engines for the petroleum engineers, so they can take an action. So that's where the AI playing the reduced order models, which we haven't talked about in this session, is playing a big role, and how AI and physics and HPC are coming together.
Great, that sounds good. Okay, we have another question. How do you apply machine learning or AI to timestamp dominated data sets, in particular data derived from production monitoring and in particular SCADA systems? Essen, did you want to take that one?
Yeah, sure. It's a great question. I think every oil and gas person has this thing in the back of his mind around how do we capitalize on the a lot of data which is already being generated by the SCADA systems or the DCS systems, and apply AI and machine learning techniques on top of them. So as Peter mentioned in his presentation, RNN, when talking about recurrent neural networks, this allows you to basically do the time sequence-based search, do the analysis. So there are two aspects of those things, right? One is you're trying to classify the events, and you want to do the segmentation of the events, okay, where they're happening, and then between you there's an anomaly. Okay, what are the outliers? And this is where it really helps, right? So how you're operating a machine or a process in a winter is different than how you're doing in summer. So there is a seasonality space to it. Or when you're running your equipment in a standby mode, they're still running, but in standby mode versus they're running in the full throttle. So there are different aspects where you can easily use AI ML techniques to identify what is how you can classify those operating modes, and then taking it further is saying, okay, what are the outliers within those? So doing any kind of an anomaly detection in those things, and then from there on, once you have these anomaly detections, you're taking it to the next level, where you're going towards the prognostics and diagnostics of those events, connecting them with the expert systems, and doing a lot of NLP processing on your existing operating manuals and everything. So the whole sequence of actions you can do, you can first apply and solve those use cases.
Sounds good. Okay, our next question is, what is the definition of a perceptron? Peter, did you want to take that one?
Yeah. So the perceptron is the same thing as the artificial neuron. Essentially, just I think the fundamental definition would just be you have a set of weights, which are just a set of numbers. They get multiplied by your input, and then you add a bias, just adding another set of numbers, and then you pass it through some nonlinear function, such as a sigmoid function or a ReLU. So that's essentially just at its core what it is. It's just multiplying your inputs by a set of weights and adding a number and putting it through a nonlinear function. Then you can learn these weights through gradient descent. But the neuron is just a single set of these weights that you multiply by your input, which is the fundamental unit of deep learning.
Great, thanks, Peter. Okay, our next question is, how do we achieve an accurate machine learning prediction if we have few sample data for the use case? Essen, did you want to start with that, and then maybe see if we wanted anybody else to answer?
Sure. So excellent question, right? I think this is something which industry faces every single day. And then the lack of, in one sense, we always say in the oil and gas, we have a lot of data. But on the other side, we don't have a lot of failure data, right? So because we are such risk-averse industry, so we may not have enough data about the failure to learn how it can fail. Or they may have some sensors issue, communications issues, or the lack of instrumentation. So there are a lot of issues where we may not have the data. So there are two ways you can approach this thing. First one, which Peter talked about, it use building a synthetic data. The synthetic data is one of the very important piece, right, which allows you to build the data set as close to real life, right? And using that synthetic data, then you can train the model and start doing the inference accurately. And this is how a lot of, if you look at in the automotive industry, you cannot run a car across the globe, every car, 8 million miles to train them. So you create synthetic data simulations and then train them. Same thing, you can do it in the oil and gas industry, to build more and more accurate synthetic data. The second way where if you have lack of data, is to go back to the basics, i.e., that is first principle models in physics, right? And the new, a new way of how industry is overcoming this thing is using physics-informed neural networks. So using physics as a basic to cover the basis of how this thing's supposed to operate, and then train it on the real life data. So physics-informed neural networks is becoming really an important branch. We have not covered this thing in this session, but something it would require a dedicated session, okay, how you can really apply physics neural networks and bring all the goodies, all the excellent work the researchers and the oil and gas industry has done building those first principle models, and apply the neural networks on top of them.
Great, thanks for that answer. Go ahead.
I can take this in a more general sense, that when you're kind of in the smaller data regime of doing deep learning, I think something that we mentioned earlier today is that a lot of times you don't tackle a problem just with your data. So what is usually done nowadays is actually that you have these large-scale models that are trained on similar data sets. So say if your problem is trying to detect something in an image, you take these models that have already been trained on large data sets of images, and then you fine-tune them. So you just take your small amount of data and you use that to try and adjust the weights in the model so that they can solve your problem. And the kind of intuition here is that when you have these models that have been trained on other data like these images, it can learn these fundamental features such as the edges of objects within an image, and there's these fundamental features that can be then used for transfer learning to try and be able to solve your problem without having to use as much data. So that's like what is mostly done nowadays. You don't actually have to train completely from scratch on your own data. You can kind of use some other information. The other way people do it is you can try to distill some of your own information into these models. So you can do a lot of feature engineering. So if you know certain properties of your input data, you can adjust what you input to your machine learning model to make it a little bit easier of a problem to solve. But working on a small amount of data in deep learning is still kind of one of the fundamental issues that's being actively solved.
Great. Thanks for those answers. Okay, this next one is more of a fundamental question. Does training involve manual involvement? Nefeli, did you want to comment on that one? And then we'll open it up.
I can also answer this one if Nefeli is having some technical issues. So there is some manual involvement. There are things called hyperparameters within deep learning that do require someone to come in and do some sort of manual involvement, but it's becoming less and less that we need manual involvement. And the idea is that with deep learning, hopefully you don't have to have as much expert knowledge when you're trying to learn these models, and it should be a little bit easier. But there is some manual involvement with trying to pick the correct architecture for your model, do some tuning of the model with the hyperparameters in order to make it learn properly, and that's where a good data scientist is invaluable.
Great. Okay. We'll move on for now. Okay, this next question. The number of hidden layers often introduces false positives. How are false positives reduced as the number of hidden layers is increased? Hidden layers also increase computation time and resources. Peter, did you want to take that one?
So what was the question about? Was it about how do we handle increased computation time?
So basically, the core question is, how are false positives reduced as the number of hidden layers is increased?
I think that question, I think I saw that one, is more around kind of overfitting. When you have these super complex models and a small amount of data, you often overfit to what you're training on, and then when you try to go and deploy to the real world, it's going to be overfit and it's not be able to predict really well. There's a lot of different techniques you can use when training your deep learning where you're just trying to regularize the model a lot. So you have different ways you can do it where your input data is being regularized, and there's different transformations such as rotating your input data, adding noise to it so it doesn't overfit to it. And then fundamentally in the architecture, there's also usually a lot of different regularization techniques that are part of it, like batch norm, or just putting penalties on the weights of them becoming too large. So there's a lot of different ways where you, as you're going deeper, the tendency for it to overfit is going to increase, but we've now have these different regularization techniques that hopefully will be able to fight that. I hope that was answering his question. I'm not exactly sure.
Great, I think so. So a good way to kind of peel back what the actual question was asking there. Okay, we have another one here. With respect to predictive maintenance, what inputs would be needed to predict remaining useful life, which is very important to the engineer? Essen, did you want to talk about predictive maintenance?
Sure. That's a loaded question, to be put this way. So remaining useful life of an ESP, I won't go into too much in detail, but there are two aspects you need to look into things, right? One is the local scenarios data and the global scenarios, right, which impact on the ESP. And so just talking from the aspect of a local scenarios, which is down to the single ESP, you're looking into the failure. So any electrical, data, sensors, any downhole gauging system, everything you would need to be part of that system. But that local data down to the single ESP, usually from the past practices, is not sufficient to predict the failure. You do need to bring in the global scenarios as well, which are impacting, and the global scenarios could be the power load, it could be the injectors in information around the reservoir. You also may need to bring in some of the reservoir information as well. So there are 2-3 core set of data which you need to have, both from the ESP specific, then all the global data about the power and water injection, and then the third is the reservoirs data set. Because what you are trying to do is predict the failure, right? And the reservoir over the time changes, and so is the performances. You're looking up the injector wells performances. So you need to combine all those three together to have a fairly accurate model for an ESP.
Great. Okay. Let's go to our next one, which is talking about NLP. So have you worked on any NLP problems, such as analyzing complex reports and then judging for compliance? Nefeli, did you want to talk about NLP in general in energy?
Hi, everyone. Can you hear me now? Is that better?
Yeah, you sound great.
Yep.
Okay, great. Actually, we will be having a webinar with a company I think in October, regarding NLP work within the energy industry. We haven't published anything yet, but the work that we're doing with this company involves going through SB papers and obtaining information not only from text, but from tables and also from images. And so we're working with them to help optimize their NLP model and move it forward. So we've done this work, we've done this preliminary work with them, and they focus in working with SPE specifically, and they have a few other customers that they're working in. But stay tuned for the next webinar that we host, and we'll do a deep dive into these NLP work that we have coming up.
So let me add something to sort of talk about the compliance area to it. So yeah, I mean, NLP is getting implemented in a lot of different sectors when it comes to looking into the compliance, right? And from the oil and gas perspective, may that be the PSM or the OSHA requirements. Companies are building models to do that. Now, one of the things which we need to consider when you're doing these NLPs, the normal natural language processing models, which is basically based on what we call the Shakespeare's dictionary, does not apply to oil and gas. So we need to have the oil and gas specific data dictionary, which you need to use to confirm and say, okay, yeah, what is happening? Is it what kind of a deviation? What kind of a compliance issues you may have? And you can, on one thing, you can have multiple documents. You can have, as I said, PSF practices. You have OSHA. You can have your own internal audit reports. Yeah. You can have any HAZOPs or any other documentation which you need to conform to and bring it in and apply the NLP and NLU. So that's one of the key things, right? The natural language processing and understanding both pieces. The third piece which in the industry is significantly heading towards is the intent recognition. Okay, what is this is currently is not, there's no compliance, but the way the actions are heading towards, you may lead towards the non-conformity of the standards. So there's a lot of research work is happening. And the other element which I would like to highlight is most of the NLP work currently which you're seeing in the industry is more of transactional work with the chatbots and things like that, where even when you're looking into the Alexas and Siris, the way you are communicating with those systems is more as in a transactional manner, where you're asking them the question about the weather, about the food and the route, and they answer you. The next generation, which is already available, which is called conversational AI, right, where you can basically hold a proper conversation and the models can retain the context of what you're talking about and what is you're asking. You don't have, so keeping the context, keeping all the understanding of your previous questions, and then answering, you're becoming very, very intelligent the way you are answering. So this is where the industry is going. There's a lot of adoption in the healthcare industry, a lot of adoption in the, especially in the compliance areas, a lot of adoption, automotive industry, financial industry. And we know a lot of our partners who are working, especially in the oil and gas domain, building those oil and gas specific models.
Great. Okay, this question I'll probably direct towards Peter. How do you monitor or control any biases or variants that may be introduced via perceptrons? And I know we talked about perceptrons a little bit already.
So I think it's just that's part of the training and validation process. As you're going through and training these models, it's not like you're training one model. You're actually having to train a bunch of different models and do some, so you might do regularization, do some feature engineering. And to do this, you need to have a really good validation set. So when you're doing deep learning, in order to be able to evaluate how you're actually going to be able to perform on some out of sample data or unseen data, you actually keep some of your data out that you've collected so that the model has not seen it. And then you use this as feedback in order to try and control this classic bias and variance trade-off. So you'd first train your model on some data, and then some of the data that it hasn't seen that you still have collected, you'd go and evaluate it on that model to see, hey, am I overfitting to the original data so it's not actually generalizing to this unseen data? Or maybe I have way too much regularization in my model so it's not actually learning what it needs to in order to perform on this unseen data. So I'd say that the main way that people do this is through keeping out some sort of validation set or doing some cross-validation like you would in any other statistics model.
Sounds good. Okay. Another question, how do you apply machine learning to recalibrate a well and reservoir model using real-time data?
Okay, I'll take that. Another great question. Seems like a lot of practitioners' questions, So what is currently happening in the reservoir, a lot of these reservoir simulation models, they're working offline, and you don't run them so frequent. So getting the more IoT, more data-driven, and bringing that current data back to the reservoir models, retraining them, this is a kind of a journey most of the software tools provider are currently on. Okay? But again, bringing data and running them is still an exercise, right? So, but this is the journey they are still heading on. A lot of them have done, and the big companies, and they are doing those things. The alternative approach, which I alluded to, and to make this the whole interaction, all these things more faster, is going towards the reduced order or low fidelity models. So you can, and this just depends upon what kind of use case you want to run based on those simulations, how quickly you want the results, how frequently in the day you want to run those things, right? And the kind of a decision you want to make. So you can run the high fidelity models, bring the data in the classical reservoir models, or the second approach is to have less accurate but a quick response coming from those models and giving you the answer, right? And physics neural networks is also one of the ways where you can train the models to learn like a reservoir model and give you the answer, with a 90% accuracy. It's like, yeah, so this is good enough for me to make a decision, and petroleum engineer or reservoir production engineer can take that decision, make that decision based on the recommendation.
Sounds good. Okay, we'll take two more questions here. Okay, for use cases such as predictive maintenance or failure forecasting, would you typically use a RNN to predict failures or autoencoding to detect anomalies? Peter, did you want to comment on that one?
What was the question there? Was it just about like which model we use, or?
Yeah, I think that's the question. Which model?
Well, so
can you repeat the question one more time? Can you repeat the question?
Sure, for sure. So for use cases such as predictive maintenance or failure forecasting, typically would you use a RNN to predict failures or autoencoding to detect anomalies?
So you can use autoencoders and RNNs. Sorry if I wasn't clear about this. Can be used together. So autoencoders is a type of model where you're just kind of compressing down the information and then re-uncompressing it in a decoder fashion in order to try and find these failure cases. But you could actually use in the encoder-decoder structure of it these RNNs. So if you have sequential data that you're trying to be able to predict anomalies in it, you would maybe use an autoencoder that has its layers being RNNs that are able to take in the sequential data, compress it down, then would decompress it with the decoder, and then use that for doing anomaly detection. So it's not necessarily that you have to use one or the other. A lot of these methods can be combined together. I'm not sure if that answered the question completely, but hopefully that was helpful.
No, I think that's good. Okay, last question here. And by the way, we have a ton of questions, so we'll do our best to respond offline, and you can also make sure to connect with all of our speakers on LinkedIn or send us any additional questions you have over email. Okay, this one is going back to physics-informed neural networks. So are physics-informed neural networks going to be more applicable than full physics problems such as reservoir simulation?
Okay, I'll take that, and probably Nifali can jump in as well. It just depends, right? The need and the requirement of high fidelity models is always going to be there. This is what we do. This industry has done, and you will always use going. When you're building a new infrastructure, you're building doing the new facility and everything. You need a high fidelity model, and you need to understand what is beneath the earth, what is happening. So you're already trying to discover something which you have not seen, right? So there's a need to do these high fidelity models. Now, as you move towards more productional use cases, more operation, more brownfield use cases, where the quickness of the response or the timing of the response is more important. So if you can inform an engineer, yes, with the 80% or 90% probability you can take this action, would be the best choice for you. That becomes kind of a recommender, right? Okay, yeah, that helps me. I have enough understanding of the system and what is giving you a second opinion. Okay, hey, you can do this thing, and this is the most possible action. So he's not making a decision in the blind. He has some physics to back him up. Okay, and that's where these physics neural networks can immensely help as they run way faster, multifold times faster, and really help in the operational decision making. I hope I answered that.
I would like to add on to that. We've done some work recently using physics-informed neural networks specifically for seismic conversion. So from there, we started with a point cloud representation. And, if you solve the partial differential equations with a numerical solution, you have to go through the grid point at every point, correct? So with a PIN, with a physics-informed neural network, we can do this a lot faster because after you've trained the model up front and you've built that neural path, you don't need to go through the grid point, and you can get to the same answer faster. So that's one example specifically for energy that we've seen that we can use that does increase time from about 2 weeks to 8 hours approximately. So we see a significant improvement time-wise. Though that doesn't lead specifically to reservoir simulation like the question asked, we are able to recreate in another domain. So we haven't done it yet, but we would be working on the next project, and we hope to see very similar results.
Great. Well, as I mentioned, we had a ton of great questions, a few left over, so thank you all for submitting those questions. We are going to wrap up now, but before we do, just want to mention a couple of things. So do make sure to reach out to all of the speakers, Peter, Nefeli, and Essen on LinkedIn or email. We also want to, again, thank Saeed and SPE DETS for helping promote this webinar. So big thanks to them and their audience for coming. Definitely make sure to check out our resources list. We've got a ton of great energy assets and also our energy webpage where we've got all of our up-to-date information for NVIDIA in the space. And as Nefeli mentioned, make sure to follow us because we'll have that NLP and energy webinar coming up in probably October timeframe. So thanks again. And this will be available on demand. We'll upload the slides tomorrow. Thank you, and definitely continue to reach out to us. So have a good day.